Hello again, everyone. In this lecture, I want to start going back to MATLAB a little bit to learn how we can use MATLAB to solve differential equations. So previously, we've discussed how to solve first-order ordinary differential equations two ways, using separation of variables and using the method of first-order linear ODEs. And in this lecture, I want to go a little bit further to think about how could we do this numerically using the computer. And the reason for that is that, if your ODE fits these profiles, if you can solve it by separation of variables, or if it's linear, then there's no problem, you can do it by hand. But what if it doesn't fall into those categories? Then you kind of have to use some other techniques. And sometimes there are no analytical techniques, you can't do it by hand, you have to put it into a computer. Okay, so learning how to solve ordinary differential equations using the computer is a useful skill which we want to develop. So let's get started with that. Just to give you a big picture overview of the first order ODEs, so let's say we have our all first order ODEs here. Let's say that every first order ODE fits into this diagram. Now there's a subset of these which is going to be linear. So we can say maybe these are the linear ODEs. Every first order ODE is either linear or nonlinear. So let's say we have some subset which is linear. And then there's also some subset which is separable. So the separable equations you can solve by separation of variables. So there's some other subset of those which you can solve by separation of variables. So this is separable. Okay. And then, of course, there are some which are both linear and separable. So there's an overlap here. So some of these equations are both linear and separable. Okay, so if your ODE is in either the red circle or the green circle or both, you can solve it by hand. You know how to do that, using separation of variables or using the technique of first order linear ODEs. But what if you're out here? So this is non-linear and also non-separable. Then you have a more difficult situation on your hands. Can't use those techniques we've already learned. And sometimes, like I mentioned before, you are forced to resort to the computer. Generally, if you can solve it by hand and you can get an exact solution, that's better. But the computer can be used as a last resort to solve an equation numerically. To solve an ODE numerically. And we're going to learn some methods of doing that. Okay, so let's think big. Let's say we can write our first order ODE in this form. It can be written like this: y dot of t is equal to some function of y and t. Okay. So I have a first order ODE, it has a derivative, y dot, in it, and then I isolate for that y dot and put everything else on the other side. Just to remind you that if this has the form, let's say f of y times g of t, in other words, if the y and the t separate or into a product of two functions, then it's separable. Okay. But let's just think in general here. And we're going to focus on initial value problems. So I'm going to focus on the situation where I know the initial time y of t0 is equal to y0. So I'm given some initial condition. This is my initial condition. And I have the ODE, and I want to solve that ODE for y as a function of t. Okay. in order to go forward, I think the best thing to do is to try to think about it graphically. So let me try to plot a picture here. So let's say this is t, and this is y. And basically all I know is that I'm starting at some position t0 and y0. So that's my initial point. And then the ODE is going to tell me how to go forward from here. In particular, my ODE looks like this, right? Let me just remind you, it looks like y dot is equal to some function of y and t. Okay. So what does this mean? I have one point already. I know the initial point. So this means that y dot of t0 is equal to this function of y0 and t0, okay? And I know the function f because I know what the ODE is. So this is known. So what is this equation telling us? Y dot evaluated at a certain point. What does that mean? The derivative of the function y at the point t0. The interpretation of this is the slope of the function y of t at the point t0. And to figure out what that slope is, I just take my function f, which I know, and plug in that initial point. So the idea is basically, I don't know what the function is, but I know there's an initial point, and I also know the slope at that initial point. So I know the slope of this, maybe it's like this. Okay. So this green line here has a slope equal to f of y0, t0, where f is the thing on the other side of the ODE. F is this. Okay. So maybe I want to figure out what is y at a later time. What could you do? You could say, okay, I'm going to approximate my function y as a line. So I'm going to take the slope and just extrapolate that slope to a later time. So let's call this time here t1. So I use the slope and I draw a line to some later time here. Let's call this t1. And that means I have a function or a point here which is called y1. How do I get y1? So I'm going to use the point slope form here of the line. So it's going to be y0 plus the slope, which is f of y0 and t0, times this distance here, or this time, let's call it delta t. Delta t. So I'm just writing down the equation for that line. I start at the point y0, t0, and I go up by a certain amount and over by an amount delta t, and the amount that I go up is controlled by the slope, which I know, which is f of y0 and t0. Okay. Now let's think about, I'm at the point t1, y1. Now what can I do? I can determine the slope at that point. So let me draw another line here. What's the slope at this point? Let's say it's something like this. This has a slope equal to f of y1 t1, right? Because once again, if I look over here, y dot of t1 is going to be f of y1 and t1. And y dot of t1 is the slope at the point t1. So I can determine that slope there. And now maybe I do the same thing again. Now I take that line and I go forward a bit to some later time, let's call it t2. And then it would have some value here, y2. And how do I get y2? I take y1 and I add the slope f of y1 t1 times that time delta t. Let's call it delta t here. Okay. Just like that. And you can imagine just keep going. I start at this first point, I figure out the slope there from the ODE, and I go draw a line and go along that line for a little ways until I get to another point. And then I find the new slope, and then draw another line and go along that line for a bit until another point, and just keep doing this until I have enough points that I'm happy, okay? You can probably see a scheme emerging here. So you see, how did I get y1? I took the previous point, evaluated the slope at that point, and multiplied by delta t. And then how did I get y2? I took the previous point, found the slope at that point, and multiplied by delta t. So you can kind of see the generalization here. Let me call it y of k plus 1. So I'm going to use k as a general index. K plus 1 is going to be equal to yk, so the previous point, plus the slope evaluated at that point, which is going to be yk tk, times delta t. So let me just put here delta t, like that. And you can kind of see this is naturally can be implemented in a loop. So I start at the first one, and then I calculate the second point, and then I do a loop again and calculate the third point and the fourth point, and so on. This is called Euler's method. It's spelled like this, so it's tempting to say Euler's method, but it's actually pronounced Euler. So Euler's method. And that's how you solve an ODE graphically. So notice, I'm not going to get the function y of t. I'm not going to know what that function is, but I will have the points. I can draw a graph of how that function behaves based on the ODE. I should be clear here that t sub k plus 1, so the next time period, this one is pretty easy, is just the old time plus delta t. So what I'm going to do is, let's do an example here. Solve, or let's say use Euler's method to solve the ODE y dot of t is equal to y plus t with the conditions y of 0 is equal to 1 from t equals to 0 up to t equals to 1 using, let's say, 10 iterations. By the way, so you're saying, like, why would I do it with this equation? This is a linear equation. I can solve this equation. I'm going to do it this way just to show you, because we can solve this one exactly, we can compare and see how well our numerical method is doing. So note, this one has an exact solution. Y of t can be solved exactly. And the solution to that is this. Y of t is equal to 2e to the t minus t minus 1. And you can check that by solving that ODE using the method for first order linear equations. Okay, so I'm just going to use this as a check. Now, a lot of times when you have to solve something numerically, you won't know the exact answer. But in this case, I'm just doing it as an illustration to show you that how it looks compared to the exact answer. So let's take a look at MATLAB. I've started something going to do this example. So here's my function f. I've defined a function f of y and t as y plus t. Okay, so this is the equation I'm trying to solve. Y dot is equal to f of y and t. And so that f is everything on the other side of the ODE. Because we're trying to solve y dot is equal to y plus t, I put in here y plus t. Okay, so if you have a different ODE, you just change this function here. Now let's start with just some basic, so we're saying let's start at time t0 is 0 up to time tf equals to 1, because this is what the question asked for. And this was my initial condition. I said y of 0 was equal to 1. So I'm putting that initial point in there. So I know the initial point t0 is 0 and y0 is 1. I'm going to pick 10 iterations And that means my time step is going to be, if I have 10 points and I'm going from time t equals 0 up to t equals 1, then I'm going up in steps of 0.1. So my time step is tf minus t0 divided by n. Okay, so these are all just kind of setting things up. Now comes the Euler's method. So I want to do this n times. What am I going to do? I'm going to go through this exact same step here, right? So I start at the first point. To find the second point, I take the first point, multiply by the slope, and then times delta t. So add the slope times delta t. And also increase my t by an amount delta t. So let's try to code this up into this loop here. I'm going to be creating a list of times and a list of y points. So I have the first point of time and the first point of y. And then I want to find the next time point and the next y point and the third and the fourth and so on. I'm going to store those in these lists. T list is going to be the list of times, and ye list is going to be the list of y points. So I know the first time is t0 and the first y is y0. So what does Euler's method tell us to do? To find the next y point, ye list of k plus 1. So that's the next one, right? The first time through k is 1. So I'm finding the second point through when I come through the loop the first time. The second time through the loop k is 2, so I'm finding the third point. So I'm always finding the next point here is equal to the previous point, ye list of k, plus the slope, which is found from this function f of ye list of k, t list of k, times this time step, which I'm calling t step. That's delta t. Just like that. So compare what I just wrote to what was on the previous slide. Here. Yk plus 1 is yk. So the next y point is the previous y point plus the slope evaluated at the previous y and t point times delta t. You can see all I did is I just translated that into MATLAB code. So ye list of k plus 1, ye list of k, plus the slope evaluated at the previous point times t step. And then I've got my next t point, that's easy, k plus 1, is equal to t list of k plus t step. So I increased my time step as well, or I increased my time. And that's it. So that should do it. Now, what I have down here is, this is the exact solution, which I will plot along with the numerical solution. And this down here is just code for making that plot. Okay, so all this stuff down here is just making the plot of the numerical solution and the exact solution. So let me run it and show you what it looks like. Here's the graph that is generated. I plotted two graphs. The black line is the exact solution. That's what we know from our first order linear method. The blue points are the points I got from Euler's method. So I took the tangent line here and extrapolated it to the point 0.1. Then I took the tangent line here and extrapolated to the point 0.2. And I just kept doing that Euler's method over and over, and I got the blue points. And you can see the blue points are doing pretty well at approximating this curve. Now, they're not exactly right, because this is just an approximation. It's a numerical method of trying to determine how that function behaves. But you see, when you try to use this in the real world, you probably won't know this black line. And then you can see that at least I'm getting a pretty decent idea of what this function is doing using this numerical method. So I get the points out of it, and I have some sense of what that function y of t is doing without actually having solved the ODE by hand. So that's an example of Euler's method. So just to summarize, we've talked about this particular recipe for solving an ODE numerically. If I know the ordinary differential equation, and I know the initial point to start at, I can use the computer to loop through and approximate the solution of that differential equation. And I did this particular example to illustrate that it works pretty well. Now, when we come back together in class, we'll start to learn how to improve this method. So can we do better than Euler's method? And the answer is yes. There's more sophisticated algorithms, but this one we'll start with to give you, because it's the easiest one to understand, and then we'll learn how to improve this in in class and in our next lab. Thanks for your attention. See you all in class. Bye for now.